So in this video, I will talk about using machine learning for factor investing. So because there is a very recent book for using machine learning for factor investing, so I highly recommend to read this book from two great authors. And of course, this is really a basic book, Asset Management, with a great author. And if you want to see the relationship with other paradigms, the relationship between smart beta, and other paradigms, you could also have a look at this great book. So we start with the standard capital asset pricing model. So we have portfolio return, risk-free, and beta, which is related to systematic risk, and also some noise. So some motivation for smart beta is that research discovered that CAPM, capital asset pricing model, does not describe market behavior. So you could define different factors. You know, currently we have more than 350 factors such as value, size, it's value, size, momentum is a little bit controversial, but you have also quality, investment, low volatility, and many others. So you see that if you use principal component analysis, you can reduce the number of your factors from 350 to maybe only 6 factors. So this is one naive approach for using machine learning for a person who doesn't really know anything about financial economics. And that's why some people use that. So you cannot justify your model because you have just used machine learning and statistics without knowing how to justify your model. So it's not interpretable, and so it could be a weakness. So the term factor beta was used to describe sensitivity to the factor, as we did like this, sensitivity to the markets. And so over time, smart beta has come to include any rule-based strategy. We often call it alternative beta because it gives us alternative risk premium instead of traditional risk premium. We have alternative risk premium. And so if you just categorize portfolio construction approaches to rule-based and optimized, you will wonder why I've done this. Because, for example, my approach is a combination of this one and this one. First, I try to maximize a utility, and then so I create a tree of decision, this rule-based decision trees and something like that. So I use a bit of both paradigms. I think it would be a better and more flexible approach. So you see, risk parity, hierarchical risk parity, all of the paradigms you can see as a rule-based. And minimum volatility, you do maximization, simple maximization, either quadratic or just first order. And so now we can see factor as anomaly. People usually say it's an anomaly. But, when we say the word anomaly, such as low beta anomaly, that I will explain in my third lecture, this is the first lecture, you will see that all of them could be proved by just maximizing your utility, which is very different in different cases because you have either included macroeconomic with microeconomic factors and models. So it all depends on your model and what you are going to prove. But usually you want to prove some anomalies and So this is just a return, and if such factors do exist, then they are in contradiction with cornerstone model in asset pricing, that the capital asset pricing model of Sharpe ratio, Mr. Sharpe. So indeed, according to CAPM, the only driver of returns is the market portfolio. This explains why factors are called anomalies. And so we have factor as anomaly. If we do regression in different time frames, it is conditional and more realistic. So we have different coefficients for different time frames. Yes, because this is in practice, it's a statistical thing. So you should do statistics. You should do inference over that. So all of the non-parametric and parametric statistics will apply. Then exactly the same way when you define your covariance. So it's very general. That's why people define different ways of calculating this statistical nature using, for example, shrinkage of covariance. For example, the famous article, "Honey, I shrunk my covariance matrix," or something like that. So all of them are in particular have a natural statistical in their origin. So simple portfolio sorts, as we do, we first rank them with their size, book to market, any factor that you like. First you do rank them, and then you put it in some based on some criterions. You put them, for example, you have just 10 portfolio. You could either use 2 portfolios, for example, high value, low value, gross and values, for example. So, and then we use the weights of stocks inside the portfolio, and finally you report the return of the portfolio. So this is the example of a size factor, the average returns of small versus large firms. And so Fama French model is just a single step forward. So instead of just model it with the market, that even this one, you are doing it wrong because, for example, S&P does not represent your market, but you do. And and also use value. So high minus low and small minus big for size. So you have three different beta, and you add some noise as well. So value is high minus low, size is small firms minus large firms. Momentum is a little bit controversial because the frequency that you do the rebalancing stuff here is different when you do size and value. And low volatility, anti-beta, I will talk about anti-beta in the third lecture. It is prior realized volatility. And finally, profitability and quality. Check balance sheet. So we want to see the robust minus weak profits. So factors. Portfolios are based on one characteristic, and the factor is a long-short ensemble of the extreme portfolio minus the opposite extreme. So small minus large for the size factor, or high book to market ratio minus low book to market ratio for value. Value, people define 4 different or even more 4 different measure for that. So if some people say book to price, earning to price, sales to price, different metrics. So when a person says value factor, you should see what's behind their model. It could be anything, and the results changes dramatically. The other one is size, and as you see, we buy the small stocks and short sell large stocks. This is when you want to just focus on one factor. For example, he is a size factor investor. But in the second lecture, I will talk that we use a combination, a multi-factor approach, which is either mixing or integrating. integrating, or mixing in second lecture. So our multi-factor is not like this. This is just a single factor. So we use a combination of size, value, momentum. And so for example, momentum by outperforming stocks and short sell underperforming stocks. We long outperforming stocks and short sell underperforming stocks. So we can see all of them in all of the factors from 1981 is my birthday, 2021, post-corona. You will see different results. So they have some correlation with each other, 2 by 3, 3 by 2. And you will see that traditional utility is like you want to maximize the return and minimize your standard deviation, and you have a risk-averse measure lambda. And in modern utility, you also consider the things that influences your expected utility, different factors. You have different KC. And multicollinearity is a problem when some of your independent variables they have some relation with each other, and so if they have some relation with each other, so you just make a relationship between your independent factors to remove that. Of course, there are other problems as well, such as heteroscedasticity. It means that. It means that, for example, here the deviation is small. Suddenly, it becomes the residual errors grows, and so we have some different statistics in order to kind of tune and reduce the bias of that. For example, we use some methods to reduce heteroscedasticity, and check it out for Fama and French. And you see, for our process is that you first prepare your data, your different prices, you make the factors, you do some processing, and you divide into training and test data. And finally, use some trees, decision trees, random forest, or gradient boosting, or you use naive neural networks, which is only good for when you have lots of observations and a few number of features. Support vector machine is great, especially if you use kernel SVM, not a simple SVM, because simple SVM is just good for linear models. And finally, you want to maximize the prediction. You maximize the expected utility, and so it's guys who like reinforcement learning and even deep reinforcement learning look at that like this. As a learning task in which parameters are chosen such that the reward is maximized.